Hi, everyone. I just wanted to say that thank you for coming in tonight. I just wanted to give us an extra few minutes just to see if anyone else wants to join in last minute. So if you hang tight, we'll get started in a few minutes. Thank you. Hi, everyone. So good afternoon. Thank you for joining this evening. We are going to get started. My name is Sarah Kahn. I'm, as you guys know, one of the PGY1 pharmacy residents. I have no financial interests or affiliation with any organizations that could be perceived as real or apparent conflict of interest in the content of this presentation. Real quick, here are the pharmacist's objectives. Objective number 1 is to describe type 1 and type 2 error, identify the difference between discrete and continuous variables, match the appropriate statistical test with the data presented, memorize how to calculate relative risk reduction, absolute risk reduction, numbers needed to treat, standard error of mean, and standard deviation. Identify if the results of the statistical test is considered significant. Biostatistics is the application of statistical principles to questions and problems in medicine, public health, or biology. Its purpose is to characterize a given population with respect to the proportion of subjects who have a specific disease state. It would also be important to estimate the magnitude of these problems over time. In other circumstances, it would be important to make comparisons among groups of subjects in order to determine whether certain exposure variables are associated with a greater risk of certain health outcomes. It would be impossible to answer all questions by collecting information or data from all subjects in populations of interest. So a more realistic approach is to study samples or subsets of population. Biostatistics provides tools and techniques for collecting data, then summarizing, analyzing, and interpreting it. If the sample one takes are representative of the population of interest, they will provide good estimates regarding the population overall. So consequently, biostatistic analyzes samples in order to make inferences about the population. So the goal of this presentation is to help introduce or to refresh some fundamental concepts and definitions of biostats that may be helpful in clinical practice or possibly for your BCPS review. So before we begin, let's look at a quick overview of a study. The first step in any research is to define a research question. Then you design the study accordingly in a way that helps answers the research question best. Afterwards, patients and studies are enrolled, and after the study has begun, data is collected per the study design. This data is then analyzed for possible publication. So without diving into the research question, let's take a look at some of the common studies we come across in practice when we review literature. Here's the levels of evidence pyramid. This pyramid allows us to see the hierarchy of evidence. At the top of the pyramid is what we call filtered evidence. This includes your systematic reviews, meta-analysis, and your critical appraisals. These studies evaluate and synthesize the literature. The top of the pyramid represents the strongest evidence. We are probably familiar with a lot of these, such as like Cochrane reviews and Dynamed. At the base of the pyramid is the unfiltered evidence, which includes your randomized controlled trials, cohort studies, case reports. These are individual reports and studies, also known as primary literature. At the very bottom, there is expert opinion articles. Let's take a look at some of the unfiltered evidence or primary literature studies first. A randomized controlled trial is a carefully planned project that studies the effect of a therapy on patients. It includes methodologies that reduce the potential for bias. So it employs techniques such as randomization and blinding. And that allows for a comparison between intervention groups and control groups. Subjects with the desired characteristics are included, and patients with characteristics that may confound the outcome may be excluded. The study is preferred to demonstrate possibly superiority in studies. It is also a study design in which cause and effect can be established. It also allows for an investigator confidence that if a difference in outcome is seen, it is due to the experimental or intervention group. Some limitations include it is actually very expensive and time consuming. Also, RCTs may not reflect real life setting. Therefore, external validity of this trial type can be limiting. However, on the flip side, it does have a high level of internal validity, as you can replicate the study under the same controlled settings and possibly have the same outcomes. A cohort study takes a large population, and then follows the patients who have a specific condition or receive a particular treatment over time and compares them with another group that has not been affected by the condition or treatment or exposure being studied. Cohort studies are observational and not as reliable as randomized controlled trials, since the two groups may differ in ways other than the variable under study. A benefit to this is that it is good for looking at an outcome if the intervention itself would be considered unethical. A limitation is that it is absolutely time-consuming and expensive compared to retrospective studies. Also, cohort studies may have many confounders, and these are difficult to control for. As a recap, prospective studies are beneficial since you can use randomized controlled trials. It can also provide information on risk. Some drawbacks is that it is time-consuming, as I've mentioned, expensive, and possibly a lot of patients can be lost to follow-up or drop out. So this is also something called attrition. A case control study is an observational study in which patients who already have a specific condition, so your case group, are compared with people who do not, so your control group. There is no randomization involved in this. These studies are usually less reliable than randomized controlled trials and cohort studies because showing a statistical relationship does not mean that one factor necessarily caused the other. These studies look back into time, and patient records are usually reviewed. Some pros for this type of study, though, is that it is more ethical. There's not a risk for experimental exposure. It is less expensive and it is less time consuming. Also, you have access to study records and you could see possible multiple causes or exposures. It's also best for rare diseases. So if you have a rare disease state, this is a good type of study to utilize. It is also easy to conduct since you have readily access availability to many resources. This also can be good for looking at outcomes when a prospective intervention would be also considered unethical. Some drawbacks is that there is bias with this, especially since you can't use blinding or randomization. You have to rely on possibly patient recall, which is recall bias as well. It is hard to select a controlled matching group. You can't establish a cause and effect reliably in these studies. And then some associations can't be made at all, so they're practically non-existent. Cross-sectional studies are point prevalence studies. It looks at a group or multiple groups over a given point in time. So this comparison is done at a single point in time. There is no before or after analysis that you may see with other studies, such as an intervention group. Some pros is that it is cheaper to do, it's easier to perform. However, follow-up is not common in these studies. These studies can be great to generate further studies. So you could do a point prevalence study and be able to generate possibly a hypothesis for other studies to be done. Some drawbacks is that it is prevalence, not incidence, and we're going to go over that more in depth in the upcoming slides. Prevalence studies can be surveys, and these are susceptible to a number of biases, especially recall bias. It does not determine causality as well. And then almost always after a study like this, further studies are always needed. Case reports and series describes an adverse reaction or a unique condition that appears in a single patient. So that would be a case report, or a few patients. So your case series. It is important to note, because they are reports or cases and no control groups with which to compare outcomes, they have no statistical validity. So some benefits of this design is to possibly identify a new disease, or to see a new side effect or potential use of a drug for a new indication. But these studies are not used for statistical validity. They are good for possibly generating a new hypothesis, like the previous study we discussed. But some limitations include conclusions cannot be drawn from a single or a few cases. Now to look at some of the evidence that is at the top of the pyramid. So a meta-analysis carefully examines a number of credible studies on a topic, and it combines the results using quantitative statistical methodology. It is a higher quality systematic review, and therefore it is at the top of the pyramid. The benefits of this study is that it could pool together smaller studies to help provide an adequate sample size. Some of the limitations is that these studies may not be uniform. So if they are taking several studies, all these studies may not be the same, and they may be ununiform in many different ways, such as each study might have a different exclusion and inclusion criteria. And the validity can be compromised if, suppose, they use those smaller studies and they weighted it the same way as a larger study. So therefore, appropriate methods need to be utilized in order to have this strong meta-analysis. So let's do a review question. A Cochrane systematic reviews are considered what type of evidence? Okay, it is considered a meta-analysis. Good job. Now let's shift gears and look at all the potential data that is used in all of these studies. Data can be considered quantitative or qualitative. Data is expressed as categorized or certain variables in studies. A variable can be considered non-metric, which is also considered categorical or discrete, or it could be considered metric, which is also referred to as numeric or continuous. I do apologize for all these labels, but different resources sometimes use different labels. Categorical or discrete variables take category or label values, and it place an individual into one or several groups. You have nominal data when there is no natural ordering among the categories. So a common example would be like gender, eye color, or your ethnicity. Ordinal data is when there is a natural order among the categories, such as ranking, scales, or letter grades. However, it is important to note, ordinal variables are still categorical and do not provide precise measurements. So differences are not precisely meaningful either, though, for example, take a look at like trauma scores. There is not a meaningful difference in magnitude, or the New York Heart Association functional classification for the extent of heart failure. Each class does not necessarily relate to the same magnitude of the extent of heart failure. This is the type of data you test for proportions and ratio. Quantitative variables take numerical values and represent some kind of measurement. This is also called continuous data, data points where there is a sense of order and rank. In addition, the magnitude of difference between each number is the same and measurable. This contrasts what we just discussed about ordinal data. It is made up of two types of scales of data, which is your interval and your ratio scale. The only difference between interval and ratio scale is whether or not the scale being referred to has an absolute zero. So interval scale data, this is when the numbers have units that are equal in magnitude as well as rank order on a scale without an absolute zero. Scales of this type scales of this type can have a assigned zero, but it will not be like corresponding to an absolute zero. So for example, your Fahrenheit scale. Ratio scale data, this is when the numbers have units that are equal in magnitude as well as rank order on a scale with an absolute zero. So your example for this would be Kelvin scale or heart rate or blood pressure. So a quick question. What type of data is considered discrete among these? Heart rate, Kelvin, gender, Celsius. Correct. It is gender. Let's look at how we can come to the conclusion that a study outcome has a statistical significance. We talk about this a lot in pharmacy practice, and it would be nice to sort of go over this a little bit thoroughly for this CE. In order to do that, let's take a quick look at hypothesis. Every study has a null hypothesis and then an alternative hypothesis. A null hypothesis is a hypothesis that says there is no statistical significance between the two variables in the hypothesis. It is the hypothesis that the researcher is trying to disprove. Alternative hypothesis states that there is a statistically significant difference between the groups. the drug efficacy is not equal to the placebo. This is what the researcher hopes to prove. When investigators design a study, they select a maximum error margin. This is also called alpha. It is commonly set to 0.05 or 5%. This is also because there is an assumption that 95% of the values in the study will fall within 2 standard deviations. In essence, alpha is the probability of concluding that there is a difference between the groups studied. This is also the probability of a type 1 error, which is having a false positive or false statistically significant test. If you look at this graph, it will show you that a 1 standard deviation is equal to 68% of your bell curve, or 68% of your projected values should lie if it is normally distributed. This is also considered a normally distributed curve. 2 standard deviations are equal to 95% of your values, and you commonly see alpha is set to 0.05 or 0.25, 0.025, double-tailed for 0.05 or 5%. A 99% confidence interval with an alpha of 0.01 is 1%. This is 3 standard deviations. Alpha, so let's look at this from a different perspective as well. So if alpha is set to 0.01, then you find that the p-value is 0.01. The chance that the result could happen by chance is 1 out of 100, meaning this is the maximum permissible error margin. Reducing the chances of type 1 error increases the chances of type 2 error, which is false negatives. This is also your beta. The only way to reduce chances of both the type 1 and type 2 is to have ample sample size. Power is the probability of accepting the correct decision and the actual correct parameter value. This brings us to the p-value and how power and alpha play into a role in interpreting the p-value. All hypothesis tests ultimately use a p-value to weigh the strength of the evidence, so what the data is actually telling you about this population. The p-value is a number between 0 and 1, and it is interpreted in the following way. So a large p-value, so greater than 0.05, indicates a weak evidence against the null hypothesis. So in this setting, if your p-value is greater than 0.05, you will fail to reject the null hypothesis. If your p-values are very close to the cutoff, so if it's around 0.05 and are considered to be marginal, it could go either way. If it is less than 0.05, this is considered a statistically significant p-value. This brings us to the concept of how to reject the null hypothesis. So you have a sample is taken, a null hypothesis is generated, to which appropriate statistical tests are done, and then a p-value is generated. This is compared to the alpha, and then it is deemed whether or not it is significant or not. If it is indeed significant, then you do reject the null hypothesis. Confidence intervals provide the same type of information as a p-value as well. It also shows the precision in your data. Alpha and confidence interval are correlated in a study. One is reported with the other essentially. So if you see a p-value, oftentimes you'll see a confidence interval. If alpha is set to 0.05, then the study reports a 95% confidence interval. So same if the alpha is 0.01, then the confidence interval is 99%. If you think back, this is quite similar to your standard deviations. Values within the range are used to determine significance if they have been reached. It is important to note that a large sample size will result in a higher precision and smaller confidence intervals. So your confidence interval is 1 minus alpha. So in order to really see what would be a statistically significant confidence interval, you'd have to look at the type of data that you're comparing. So if it is a means data, then the confidence interval should not include a 0. So here's an example. If you have a confidence interval that's 95%, and then you have this value 100, and then this confidence interval between 80 to 120, this is statistically significant. It does not contain a 0. However, if you're looking at ratios, if you think about it, your odds ratio, hazard ratio, relative risk, don't worry, we're going to be calculating those here in a couple minutes. That confidence interval should not include a 1. So if you look at the example, a 95% confidence interval with 0.92, however, if you look at the confidence interval of 0.61 to 1.29, this is not statistically significant. Even though the value of 0.92, whether that was a hazard ratio or relative risk, the confidence interval includes a 1, therefore it is not statistically significant. I wanted to quickly distinguish between standard deviation and standard error of mean. This may come up on some of the tests, so it might be good to mention it. The standard deviation quantifies the average variation among a set of values, while the standard error of the mean estimates how precisely the sample mean captures the population mean. So you're taking the sample mean and you're comparing it to the population mean. The SEM is calculated by dividing the standard deviation from the square root of a sample size. However, the mean and the standard deviation are considered descriptive statistics, whereas standard error of mean is a descriptive of the random sampling process. So if you wanted to categorize that in your head as descriptive statistics versus random sampling, then that you might want to take that into consideration if it's better for clarity. Let's look at the types of error that could occur in a study. So alpha is the probability of type 1 error. We mentioned this. We have determined that it is already established at the beginning of a study, and it is 1 minus the confidence interval. Type 1 error is when the researcher sees a false positive. So they fail to reject the alternative hypothesis. Beta is the possibility of a type 2 error. That is that researcher sees a false negative and they fail to reject the null hypothesis. And I think I've said this before, power equals 1 minus beta. So it basically means 1 minus the probability of a false negative. Let's look at a quick question. A researcher failed to accept the null hypothesis when in fact the null hypothesis is correct. What type of error is this? It is type 1. Please let me know if I need to clarify this subject matter. I would be happy to go over it. So far we have discussed data variables, study designs, null and alternative hypotheses, types of errors, statistical significance. Now let's look at how all this is put into test and what is needed to select the appropriate test. We will try to keep the next few slides pretty simple, as this is usually pretty confusing as it is. The first thing to do when you are trying to select a statistical test is to determine what type of data you have. So continuous versus categorical. Then it is to determine if the data is normally distributed, so like that bell curve we were looking at, followed by how many samples you have in a study. So if you look at continuous data, which is your interval and your ratio data, you determine if it is normally distributed bell curve. So that is considered a parametric. Parametric means that it is normally distributed data. Accordingly, you determine the number of samples that you will be comparing. So a paired test for a continuous data is a one sample test that looks at the same group before and after a study. The same group is compared to itself, so it's considered a paired t-test. A student t-test is looking at continuous data that is normally distributed but has two samples. So you could have a treatment group and a control group. Continuous data that is normally distributed that has 3 or more samples, most of the time you're using a ANOVA test. And this is really to look at multiple variables and to compare them. Non-parametric data is not normally distributed. There is no perfect bell curve with this type of data. Therefore, different tests are used. The concept, however, remains the same. One sample, it's compared to itself before and after. And this would be your Wilcoxon signed rank. It's a one sample test. It is comparing the same group of people before and after. Two samples, you could use a Mann-Whitney test or Wilcoxon rank sum. Different from your signed rank. This is rank sum, and this is looking at 2 treatment groups. 3 or more samples, you could use the Kruskal-Wallis test. Now let's look at categorical data. This is nominal and ordinal data variables. They do not have to be distributed parametrically. The idea, however, still remains the same. You determine the number of samples and accordingly select the right test. So if you have a 1 sample, you could use a chi-square. If you have 2 samples, you could use a chi-square or a Fisher's exact, and I think that you would use that for nominal data, or you could use a Mann-Whitney or Wilcoxon rank sum, which is for ordinal data, using 2 samples. 3 or more samples, you could use the Kruskal-Wallis. If you're a little confused, it's okay. I had to look at this twice as well. Wilcoxon signed rank is for 1 sample looking at before and after measures. Wilcoxon rank sum is 2 samples preferred for ordinal data. Non-parametric continuous data and categorical data with 3 or more samples uses the Kruskal-Wallis test. Other tests that can be used to help illustrate other needs in a test. So correlation is a statistical technique used to determine if one variable changes based on another variable. This is illustrated by the symbol rho, or the Pearson's correlation coefficient. This test shows the strength and direction of the relationship between the 2 variables. This test does not prove causation though, but that there is a possible correlation. Correlations can be positive in effect, or it could be negative, or there could be no effect at all, or no correlation at all. Correlations can be, if you look at the positive correlation, so if you look at rho above the first graph, it is +1. The correlation is positive. You have a independent variable that with the dependent variable has a positive correlation. It's a +1. If you look at the second graph here, it's a negative correlation between the 2 variables, and the rho is considered -1. This is to demonstrate that there's no correlation exist at all between the 2 variables. Then there's the coefficient of variation, or rho squared. This explains how much variation there is by the rho. This is calculated by dividing the standard deviation with the mean of the variable. So, for example, if your coefficient of variation is 0.25, then you know that the standard deviation is 25% of the means. This is your variance. And this is to look at data normally. So when I was describing some data is not normally distributed, you do this type of test in order to see it from more of a normalized perspective or normalized data graph. Now let's look at regression. Regression analysis is for more than one or more independent variables. This is commonly employed in observational studies to control for confounding factors. So in order to do that, to do a regression analysis, you would have to look at your data first and then accordingly select the right type of regression. So if you have continuous data, it would make sense to use a linear regression analysis. If you have categorical data, you would use a logistic analysis. And then if it's categorical data for survival, which is completely different, you would use a Cox regression analysis. So far, we have looked at a lot of tests. However, there will be times when a lot of calculations are needed to help understand the significance or possible clinical significance of the data presented. For that, biostatistics employs epidemiological tests that can help describe risks or benefits associated with a certain exposure or treatment. First, let's look at incidence versus prevalence. Incidence is the number of new cases found during a particular interval of time. So for example, the incidence of swine flu in 2019 is 50 out of 10,000. So that is an incident rate of 0.05%. And this is describing over a period of time. Normally, incidence is described over 1 year. Prevalence is the number of cases, new or old, found at a particular point of time. So for example, on June 1st, 2019, 4 people had swine flu. So the prevalence rate on June 1st, 2019 was 0.04%. This is a simple contingency table. It's a 2x2 table. We've all seen it, I think, at some point in our careers. It is frequent. We're going to be referring to this table frequently for upcoming calculations. I just wanted to point out the event and no event cells may change a little bit throughout the slides. Just pay attention to it. I will try to call them out as I go. So on the top, you have events versus no events. And then on the side, you have your cases and controls, and then your totals. So the first calculation we're going to look at is relative risk. And this is looking at the incident risk among an exposed group versus the incidence risk among an unexposed group. So how to calculate that? You would take your cases and you would do the number of events divided by the total amount in the cases. So if you have A plus B would be the total amount of cases. Then you have your controls. In controls, you have C number of events, and you would divide that by C plus D. And then accordingly, you would take the risk in the cases, and then you would divide that by the risk in the controls. How do we interpret relative risk? So if relative risk is equal to 1, there's no evidence of an association to the event or exposure. If the relative risk is greater than 1, then that exposure is potentially harmful. If the relative risk is less than 1, then the exposure may be protective. So if we take a look at this graph, and I've put some numbers in, and if you wanted to do the math, you would do 3 divided by the whole number of cases, you have 100, and then you would do 8 divided by 100, which is the number of controls, you get 0.3 0.75, which is equal to 37.5%. So interpreting the results, you have 0.375 as your relative risk, which means that there is fewer events in the treatment or the cases group. So this exposure to this particular variable may be considered protective. How would you like to describe that? As relative risk in the treatment group is 37.5% compared to the control group. Now let's look at relative risk reduction. That is taking the incident risk in the exposed group minus the incident risk in the unexposed group divided by the incident risk in the exposed group. Or you could take 1 minus the relative risk and you could get the same answer. So if you did 1 minus the 0.375 that we calculated in the previous slide, you would get 0.625, which is the relative risk reduction, or 62.5%. So relative risk reduction, 37.5% relative risk of having an event with the treatment group is equal to having a 62.5% relative risk reduction with the treatment group. The reason why I'm going over this is that if you do have questions that come up, this is the type of lingo that they would be using. It would be important to be able to distinguish what or how to interpret those values. Absolute risk reduction. It's the incident in the control group minus the incidence in the exposed group. This has to be an absolute value. This is never a negative integer. So if you take a look at our example, you do 3 divided by 100 minus 8 divided by 100, you get 3% minus 8%, which is 5%. It has to be, a positive value. It would not be negative 5%, it would be 5%. Numbers needed to treat. This is a number of patients needed to be treated or to have that exposure for the disease or the event to be prevented in one patient. So you take the absolute risk reduction, 1 divided by the absolute risk reduction equals to the number needed to treat. So if we went back to our current group of people, and these are just random numbers I put in, so 1 divided by 0.05, you get 20 people. So you would need to treat 20 people to prevent one event. If this value is not a whole number, so for example, it's 303.2, you have to round up. The number needed to treat would be 304. That is because you never want to overestimate the efficacy of any treatment group. Attributable risk. Attributable risk is the incidence of disease or event attributed to the risk factor minus the incidence of the disease in persons not exposed to the risk factor. So a lot to sort of say, but it's basically like the absolute risk reduction, but it's looking at adverse events particularly. So you would calculate it like an absolute risk reduction. However, this is for adverse events. And I tried to highlight that those events would be adverse events. Numbers needed to harm. Numbers needed to harm is calculated by doing 1 divided by the attributable risk. And this is basically like numbers needed to treat. However, if the value is not a whole number, so it's 303.2, you round down. You never want to underestimate the risk associated with a drug treatment. So odds ratio. Odds is the probability of an event divided by the probability of a non-event. So it is important to realize the ratios that we were talking about earlier. Odds ratios greater than 1 indicates an increased occurrence of an event. Odds ratio less than 1 indicates decreased occurrence of an event. It could possibly be considered a protective exposure. Sensitivity and specificity. These are usually regarding a test, and it possibly comes up a lot during looking at primary literature. So high sensitivity is a high level of detecting the disease. So all patients with the disease will test positive. There are no false negatives with regard to a highly sensitive test. You can rule in a diagnosis. You can't diagnose based off of this, but you can start to consider that diagnosis if you use a highly sensitive test and a test positive. A highly specific test means that there is a high level of detecting who do not have the disease. So all patients without the disease will test negative. You can rule out a diagnosis. There will be no false positives with a highly specific test. Let's look at an example of this. So a D-dimer is a sensitive test for detecting a possible clot or risk. It is not specific though. So if you came back with a high D-dimer, it is not specific, but there is a possibility that there is some sort of clot formation going on. And specific tests would be your ultrasound or Doppler. This is specific for diagnosing a PE versus a DVT. Okay, a highly specific test increase the risk of what type of error? Is anyone guessing? Okay, so a highly specific test increase the risk no? No one? Yes, Verona is correct. It is false negatives. Thank you, Verona. Okay, so let's look at a different set of information. That covers our biostatistics portion of this talk. However, a large part of BCPS or some information that we do come across is pharmacoeconomics. This is a description and analysis of costs and consequences of pharmaceuticals or their services and how it affects individuals, healthcare systems, and the society. These costs and consequences typically include both economic, clinical, and humanistic assessments. It's a subdiscipline of health economics. It uses cost benefit, cost effectiveness, cost minimization, cost illness, and cost utility analysis to compare pharmaceuticals and treatment strategies. This is really valuable information for decision makers with regard to allocating limited resources. An economic, clinical, and humanistic model is employed. Economic outcomes are looked at. So this is looking at direct, indirect, intangible costs compared with the consequences of a medical treatment alternative. Clinical outcomes is medical events that occur as a result of a disease or treatment. Humanistic outcomes are consequences of the disease or treatment on a patient functional status or their quality of life measured along several dimensions. So it could be physical functioning, social functioning, general health perceptions, or their well-being. The test can also ask for what type of costs that are associated. So you have your direct medical costs. These are costs incurred for medical products and services used for the prevention, detection, and treatment of a disease. Some examples of this is like the direct cost of being hospitalized, the drugs that are used, the lab testing, the supplies used. Then there's direct non-medical costs. These are costs for non-medical services that are a result of an illness or disease, but do not involve purchasing medical services in particular. So an example of this is that if a patient has to purchase special food, or if they need special transportation or the healthcare that they need to go get. Indirect costs are costs of morbidity and mortality resulting from the illness or disease. So this is what we consider your loss of productivity, or perhaps a premature death. Then you have other associated costs that we are not going to discuss thoroughly, but it's intangible costs such as your cost of pain, suffering, grief. You have incremental costs, which are additional costs incurred after having an additional unit of benefit from a said alternative strategy that you've used. Or you have opportunity costs, which is the value of the next best use that is also foregone. Perspectives. The pharmacoeconomic question being asked usually determines the appropriate perspective or viewpoint to be used. The patient perspective is usually the cost, what they pay for a product or service. So this is a direct cost to them. Providers, the healthcare professional or care organization, costs are the actual cost of providing a product or service. Payers, their perspective are usually the insurers, the government, employers. These are the costs that are charges for healthcare products and services allowed. Society, these are costs that include patient morbidity, mortality, and overall cost of giving and receiving medical care. This is the preferred perspective for cost efficacy analysis. So the first analysis we're going to look at is cost of illness. The methodology is considered cost of illness. The cost or the unit that they input is for costs in general are dollars, and across the board they're going to be dollars for all the tests that we're going to discuss. Outcome unit, it's not assessed. Basically, this is looking at the total cost of a disease. So what does it cost to be a diabetic? Cost minimization analysis. This is comparing groups assumed to have equal outcomes, but the only thing that's different is the actual acquisition cost. So for these analysis, you want to determine the least costly alternative. So you look at generics versus brand. A cost-benefit analysis. This is looking at outcomes in monetary sense. You could do a cost-benefit ratio. This is really beneficial when you want to allocate scarce resources. Then you have a cost-utility analysis. That's looking at quality-adjusted life years, so QALYs. These are very popular, I think, in questions, so this is an important one to sort of review. But the example is to compare treatments with respect to the quality of healthcare and patient preference. So if drug A is as efficacious as drug B, but drug A has less side effects, then that might be more preferred because it improves their quality of life. This is used because sometimes it's difficult to express certain outcomes in monetary terms. Then you have cost effectiveness analysis. You look at dollar units compared to natural units. So this is looking at, suppose, achieving your blood pressure goal. You use this to compare treatments to the therapeutic outcomes. Thank you so much for listening to this very long biostats and pharmacoeconomic talk. But if anyone has any questions, I am happy to take them right now. Everyone asleep? Okay. Well, Let's just take a quick look at some of the post-assessment questions. This is our first post-assessment question. Here's our second post-assessment question. Our third. Here's the fourth. And here's the fifth assessment question. Is there anyone on the chat? Nope. Okay, I think that concludes this CE. Thank you for bearing with me. I hope you were able to learn something. Oh, thank you. Thank you, Amanda. But I hope you guys have a great evening. If you guys have any question, I love talking about this stuff, and I'd be happy to talk about this with really anyone at any time. But thank you guys. Have a great evening.